welcome to my talk. I'm really glad to be here today to talk to you about CI Fuzz, our fuzzing platform, and show with live and practical examples how it enables developers and companies to integrate fuzzing into their development process. So I am Khaled, one of the co-founders of Core Intelligence. And before starting Code Intelligence, my research was mainly focused on binary code analysis, meaning developing techniques to assist analysts in reverse engineering binary code. And I also worked as a malware analyst using and developing several static and dynamic analysis, malware analysis techniques. And in our research projects, I worked closely with the industry, and one key observation kept appearing is that while analyzing malware and security incidents is quite important to understand them and develop countermeasures, automatically finding and fixing vulnerabilities that enable these incidents to happen in the first place is crucial. And there in these projects, I saw a huge potential in fuzzing as currently the most effective method to find vulnerabilities. But on the other hand, it's, as we also heard in the other talks, fuzzing has not yet seen a wide adoption in the industry. And therefore, we decided to start Code Intelligence with the vision of enabling companies to easily integrate fuzzing into their development process. And in this talk, we'll go through three practical use cases that represent often occurring patterns or scenarios when we work with customers, and we'll show how CI enabled them to benefit from fuzzing. So let's meet Max. Max manages a software development team, and they want to use fuzzing as soon as possible. However, they have very strict deadlines regarding their feature roadmap. And although their team, they have wonderful engineers, but they don't have fuzzing experience. So they have several challenges when they want to integrate, if they want to integrate fuzzing in the development process. This includes continuous fuzzing in the CI/CD, so continuously fuzzing the software so that the software is fuzzed with each commit. You also would like to have an easy way to understand, to analyze, and fix the bugs. The second challenge is the changes that they had to do to their build system. So in order to use feedback-based fuzzing, we need to instrument the code. Meaning, and for this, we need to use special compilers and special compiler options. And these options, this set of options, is different for each fuzzing engine. And in this project, there are several submodules. Some of these, they use different build systems, and in some cases, the compiler and the compiler options are hard-coded into the build scripts. So the build system is not quite configurable. And this proves to be one of the largest roadblocks that hinders companies from adopting fuzzing. And then the third challenge is that you have to manually create the fuzz tests, meaning that you need to know the exact compilers, the compiler options, and all the dependencies that are needed to build the code. And so with available open source fuzzers, Max has to solve these challenges on his own, basically. And now let's have a look how these challenges are solved by CI Fuzz, where we make fuzzing more acceptable for both developers and the management. So here we see sort of the complete workflow of when fuzzing is integrated into the development process. So first, we do some initial setup, we create the fuzz test, and then with each commit, with each code change that comes to our repository, the CI pipeline triggers fuzzing, meaning that we instrument the code, we fuzz, we get the report, and then if bugs are found, we analyze these bugs and fix them. And let's start from the end goal here. So what to do when fuzzing finds a bug? So basically, you want to be able to easily understand the bug in order to fix it. And a great advantage of fuzzing is that it provides a proof for each finding, meaning it provides a concrete input that triggers, that reproduces and triggers the bug. And this means that a developer can simply start his software in a debugger and have a look at what happens at runtime. And CI Fuzz enables developers to start a debugging session in their IDE from the CI/CD pipeline with few clicks. And I'd like to show that an example. So here Zend is an open source C project that we fuzzed and found security vulnerabilities here. And we configured fuzzing here so that using GitHub actions, so that the fuzzing is triggered on pull requests. And here, if we go to the pull request, we see that that it's failed. By clicking here, we see that that CI Fuzz found a crash, found a stack buffer overflow, and we get also the corresponding coverage report. So now, if I want to see a more detailed information on the bug, I click here on View Finding, and I get to see a crash, a bug report in the CI Fuzz platform. So here we get a detailed information, and I have this debug in VS Code. So by clicking here, we get a debugging session in the IDE for this fuzz test using the input that the fuzzer found in a CI. So I can do that right now. Okay, so now I am already in the fuzz test. I see the concrete input, and the breakpoints were automatically set, so that from the stack trace that we get from the fuzzer. And now I can simply go through the code, inspect the runtime values of all the variables, and this makes it much easier to understand the bug. Now we saw how easy it is to, with a few clicks, you can go from the finding in the platform to a debugging session locally. And of course, here is with GitHub is an example, but the integration is CI agnostic, meaning that it can be used with other CI solutions like GitLab CI and Jenkins. So, and what we saw right now is the bug report, and that this takes us to the previous steps, which is reporting. And with reporting, you would like to see like an overview of all the fuzzing runs, and do some filtering for certain filters, and then export the report if that's needed. And let's see how this looks in the platform. So here I am in the CI Fuzz platform. I see that the last run has failed and it found one vulnerability. I see here I can show some specific runs, or I can show all the runs, and I can filter for some criteria. And then if I need to print a report or export it as a PDF, this is also quite easy. So we saw how reporting looks like. Let's move to the more interesting part, which is the actual fuzzing. And here, so the CI/CD integration. First, the CI pipeline triggers fuzzing, where we start the regression test to make sure that previous or past errors don't happen again, and then actual fuzzing starts. And there we combine several techniques to ensure effective fuzzing. So for example, we perform ensemble fuzzing, meaning that we combine several fuzzing strategies at the same time, collaboratively, so that they share their findings. So if one fuzzing engine finds an interesting input, this input is then shared with the other strategies. And here, for example, we use as fuzzing engines libfuzzer, AFL++, and HonkFuzz, and recently SimCC is added as a concurrent execution engine to even enhance the performance. And then by running fuzzing in the platform, it's quite easy to scale the fuzzing runs and to monitor them as well. And let's see how this looks in the platform. So here I can simply go to the configured runs, and I see all the past runs. One can see some metrics like about code coverage and how many inputs were found, etc. So this is something, and here you can see, all past runs. So now we have seen how fuzzing actually works, but in order to do that, we need to instrument the code. And we said we combine several fuzzing strategies together. So there, it's important to instrument them for the different fuzzing engines. And as discussed in the previous slide, this manually changing the build system for instrumentation is one of the largest roadblocks that we see at our customers. So in order to address this challenge, we built a fuzzing-aware build system interception framework. What this means is that we run the original build system unchanged in a control environment, and then we monitor and track all compiler invocations. And then before we allow this invocation to actually to execute, we perform on the fly all the necessary changes that are needed for instrumentation. So we can change some compiler options, we can remove some, add some, we can even change the compiler, and we do this on the fly. And this has two advantages. First, you don't have to touch your original build system. You can use it unchanged. And second, you don't have to be aware of the options that are needed for each fuzzing engine. So you don't need to be a fuzzing expert in order to use fuzzing. And I'll show here how this looks in CI Fuzz. So now let's go back to VS Code. Here we see the source code of the project that we just tested. And here we see this the fuzz test that's configured, and then I can simply here we didn't change the build system in any way, so we're using the original build system. I can click here on start. This would start the build pipeline. It will instrument the code automatically using this build system interception framework, and fuzzing would be run. So let's see this in action. So code is built, fuzz target fuzz tests are built, and then a fuzzing run is started. So I didn't have to change anything in the build system. So here we saw how we automatically instrument the code without having the user to change their original build system. And then, but in order to perform fuzzing, we need to create the fuzz tests. And this is also proves to be a challenge, because there you need to be aware of all the dependencies and the compiler options that are needed to compile a certain module. And we in CI Fuzz we automatically resolve the dependencies and the compiler options that are needed for a certain fuzz test. And let's see this in action. So here I'm back to the source code. In this project, we have unit tests, and I can click here. I see this unit test testing an encoding function, and you know anything that has something to do with encoding, decoding, parsing, it needs to be fast. So I can click here to go to the definition, and here I see this fuzz function annotation that's added to each function definition. I can click here, and what this does, it automatically creates a fuzz test, and it automatically resolved all the includes that I need in order to call this function. And we automatically also resolved all build dependencies. So all the user has to do then is taking this data that the fuzzer provides and forward it to the API he wants to test, and that's it. And here it's important to notice that we don't only support row buffer, so the user can give here any data type. He can give a C struct, for example, and then what happens in the background is that we analyze the struct, the AST of the struct, and we generate grammars for that automatically, so the fuzzer will generate valid structs all the time. Here we show how we automated the process of dependency resolution and also resolving the compiler options, but how we were able to do that. And this is done in an initial setup where, and back we also use our build system interception. So we build the project once, and then we keep sort of a compilation database of all compiler and compiler commands, so that we can know exactly which dependencies are needed to compile each source code. And in order to do that, in CI Fuzz, it's just a simple initial setup step where we only need to know how the code is built, and based on that, just to run the original build system and build the compilation database. And this is all what we need to know in order to do the next steps. Here we saw now a complete workflow of how to integrate fuzzing using CI Fuzz into the development process, how we automatically create or semi-automatically create the fuzz test, we automatically instrument the code and perform effective fuzzing, reporting, and will make it easy for developers to debug the findings. And with that, let's move to our second use case, and let's meet Bill. Bill works on an old code base that lacks unit testing. And the code base represents a networked application, and with a size that they have some few millions line of codes, and several components grew historically, and they have monolithic design, meaning that it's not easy to run separate modules in isolation while mocking external communication. So what they perform there is perform system tests by directly sending requests to the applications through sockets. And they do this in this context. They simulate some valid and invalid communications with the system, and they want to integrate fuzzing on the system level, meaning instead of predefining these communications, the fuzzer should be able to perform that in a smart way while getting the feedback from the application to be more effective. So in order, here we see the exact same workflow, the same steps, and the only different step with CI Fuzz is how we create the fuzz tests. And here we automatically generate the fuzz test for Bill. And let's see how we do that. So let's. I'll move to a second project. Slide TBD. It's a web server, and that expects connections on a socket. And there, all I have to do is provide some configuration for CI Fuzz, and the fuzz test will be generated automatically. So here I can say, okay, I want to create a new fuzz test. And since I know it's a network application, I can say I would like to create a network fuzz test. And all I have to give is the server binary and the socket type. So TCP, UDP, Ethernet, or CAN bus is especially interesting for automotive software, and provide the socket number. And I can also provide the protocol. And if if I select the protocol, then CI Fuzz would know how to communicate with the server using some built-in grammars. And so with this, what used to take us like 2 or 3 weeks to fuzz network applications, as we saw in Zirko's talk and Zorikata, we can do this now with just a few clicks. And this is all I have to do in order to generate a fuzz test. And what happens here is that the server would be started in a different thread. And then the fuzzer waits until the server is ready to accept connections. And after that, it just communicates with the server and sends the fuzzer generated input. And this is one example of how to create fuzz tests without having to write any piece of code. And so let's, now with that, let's move to our third use case and meet Amy. Amy develops web applications in Java. But the thing is, so when we usually talk about fuzzing, we usually mean C and C++ applications. But with Lisa, with Amy, and since she's developing a web application in Java, we have a new classes of challenges. So first we have, it's mostly in Java, so we need to instrument Java bytecode. The inputs that are expected there are highly structured input, as in REST APIs, for example. And we want to find different classes of errors, different than in C and C++. And we were mostly interested in, for example, in the Opus top 10. So again, we have the exact same workflow, and the only difference also here is how to create a fuzz test. So what we do is we perform an automatic endpoint detection, meaning that we automatically detect the endpoints of an application, so the URLs based on which we can access each endpoint, and we also analyze the structure of the request that each endpoint expects. So, for example, a POST request that expects a JSON body, we analyze the structure of the JSON body, so that the fuzzer can automatically perform structure-aware mutations for the request and generate valid requests. And for most popular frameworks like Java Spring Boot, this process is completely automated. If for frameworks that we don't support, your user can provide a swag definition. And again, here the fuzz tests are generated completely automatically. So let's have a look how this looks in CI Fuzz. So I open our web code, which is a Java application, says Spring Boot, written in Spring Boot. And all I have to do is, okay, so I want to create a fuzz test. And since it's in Java and it's a web application, I select Java Web App Fuzz Test. And I see here the list of controllers that CI Fuzz automatically resolve in the initial setup. And all I have to do is simply select which controller I want to fuzz, and then CI Fuzz will automatically generate the corresponding test. And for web applications, usually you are required to log in before you start communicating with the application. And here, this can be easily configured in as part of some initial setup. So with that, we saw with CI Fuzz, we helped Max is happy now because he has integrated fuzzing into his fuzzing process. Phil is happy because he was able to perform system tests on his old application, and Amy was also satisfied because she was able to fuzz its web application. And the net result of that is that we have more stable and secure software while saving both time and money. So what's next? So we would like to give an limited early access to our CI Fuzz software as a service platform, and it's completely free. If you have a project in GitLab and GitHub, or you have a C, C++, or Java project, you can apply now, and this will be available soon. So you just apply now and provide us with some information about your project, and we'll get back to you. And so basically, as a conclusion, we saw that fuzzing is superior for bug finding, and CI Fuzz enables an easy integration for fuzzing in the development process, and get in touch with us for an early access to the CI Fuzz platform. And with that, I come to the end of my talk. Thank you for your attention, and I would be happy to take any questions.
All right. Yes, again? There were a few questions coming up during the talk. One of them is, which language does support?
So say again, the language that we support?
Yeah, exactly, the languages.
Yeah, so basically support C, C++, any language that can compile to LLVM. And for Java, Java and Kotlin, any language that that's based on the JVM. So basically, because we instrument the JVM bytecode directly, and recently we also added the support for Go.
Another question is, which runtimes are supported? Like, you answered some part of this question, but the question is specifically after runtime.
Can you say again? I didn't hear you well.
Which runtimes, like I think Mono or whatever, are supported?
Which runtime? I didn't get the question actually.
The whole question is which languages / runtimes are supported.
I mean, there's a question about .NET. I'm not sure if this is, I see. Okay, for .NET is planned for next year. For now, we support Java, Kotlin, anything that can be compiled to JVM instead of the LLVM languages and Go.
Another question is, do we have to use Visual Studio Code, or can it be used over command line?
Well, we have a command line tool, command line tool to interact with the fuzzing platform. So you don't have to use VS Code for that. But for VS Code, you have functionalities like debugging and fuzz dysfunction, and it's easier to interact with the platform.